In the previous video, we developed a cost function, j of theta, that we said we're going to use to fit the parameters of linear regression. In this video, we're going to develop an algorithm called gradient descent for minimizing a cost function j of theta. Let's formalize our problem. Earlier we defined a cost function j of theta, and what we'd like to do is minimize as a function of j of theta, or in other words, define the parameters theta that achieve the minimum of j of theta. The idea of our algorithm of gradient descent is going to be as follows. We're going to start with some value of theta, and so you can start at any value, but one value you could start at would be the vector of all zeros, which I'm going to denote with the 0 and a little arrow on top. So this is the vector of all zeros. And then what gradient descent does is we will keep changing theta to reduce j of theta until hopefully we end up at a minimum. Okay. So start with some value of theta and then keep on changing theta to reduce j of theta. Let me show you a let me show you an animation of gradient descent. So here's a function that we might want to minimize, and keep in mind what the axes are in this function, right? So on the vertical axis is j of theta, is the function we want to minimize, and on the horizontal axes are theta 0 and theta 1. These are the parameters of linear regression, or more generally, they're the numbers we want to change in order to try to minimize our function. What gradient descent does is it starts at some point, let's say this point over here, denoted by the little cross. And if you imagine that you're physically, if you imagine that this is the 3D surface of maybe some, I don't know, hilly countryside, and if you imagine that you're actually physically standing right at that little cross, what we're going to do is look all 360 degrees around us and try to find out what is the direction, so that if I were to step downhill, take a small step downhill in some direction, I end up reducing j of theta, or I end up going downhill as much as possible. And so starting from this cross, if you look all 360 degrees around you and take a small step downhill, you end up taking a small step in that direction. And now imagine you're standing on this 3D surface on this hill at this new point, and we're going to look all around us and decide what direction to step in next so as to minimize j of theta as much as possible. We'll take another little step downhill like so, and we repeat from the new point, and we keep on taking steps until we get to a local minimum down here. Now imagine one of the properties of gradient descent is that depending on where you started, you can end up at different locations. And so imagine that instead of starting at this position, which is where we started just now, imagine you started over a little bit to the right, that second cross up there. If you start gradient descent from that new point and you stand there, look around, find the direction of steepest descent, take a step downhill, from there take another step downhill. If you apply gradient descent from this new point, notice how you can end up at a completely different local optima over here to the right instead. And so gradient descent is an algorithm that we say it is susceptible to local optima, or the local optimum you converge to, depending on the function j of theta. It may depend on where you start. We'll come back to this later, but let's go ahead and formalize how to implement what gradient descent does. So let me write down more formally what one step of gradient descent is. Let's see. Let me write down more formally what gradient descent is. So in the gradient descent algorithm, we're going to repeat until convergence. And we're going to update theta j, our parameters theta j, as theta j minus alpha. I'll define a couple more of these terms in a second, and we do this about j. We actually say more about a couple of these things later. Okay, so let's see. This colon equals notation, right, is the notation that I'm going to use to denote assignment. And in particular, if I write a colon equals b, what that means is if a is a variable in my computer, I'm going to take the value of b and use that to overwrite the value of a. Okay, and so a colon equals a plus 1. This means increment a by 1. In contrast, if I write a equals b, then this is an assertion of truth. So this is making a mathematical statement. I'm claiming that the value of a is equal to the value of b. Whereas this thing on the left, this is assignment. Whereas on the right, this is an assertion of truth, or a truth assertion. Okay, and therefore, whereas I might write a colon equals a plus 1 to mean increment a, hopefully I won't ever write a equals a plus 1, because that's just false, right? That's just never correct. Okay. The other piece of notation is alpha, and this is a parameter of the gradient descent algorithm. And alpha is called the learning rate, and this controls how big a step we take in the direction of steepest descent. Okay, and I'm not going to prove it mathematically here, but it turns out that taking this gradient descent step, it turns out to be this turns out to be mathematically the right thing to do in order to take a step down. I'll say just a little bit more about this in a second. Finally, one last detail is this is my update to theta j, right? And so what I'm going to do is update parameters, or the update is carried out simultaneously for all theta 0, theta 1, up to theta n, or whatever the dimension of theta is. And what I mean by that is I'm going to compute the right-hand side, abbreviated to RHS, and we'll compute the right-hand side, for all values of I. And then having done that, I'm going to update all the theta I simultaneously. Okay, so this is the gradient descent algorithm. What I want to do next is just give a little bit of intuition about why taking this derivative term might be the right thing to do, and why taking this sort of a derivative may, would tend to cause our parameters to move towards the minimum. And to do that, let me use a one-dimensional example where theta. So why is it that right, updating theta using this partial derivative term, why does this reduce the value of j of theta and help move us towards a minimum? So let's look at a simplified example to gain some intuition about that. So suppose that we have a function j of theta, right, where for this example I have theta being just a row number rather than a vector. Then one iteration of gradient descent would update my parameter, my row value parameter theta, as follows. Right? And here I'm using dd theta instead of the partial derivative symbol, because theta is just a row number rather than a vector. And so let's see. Let's say I start off my value of theta at this point, right? So if you imagine I'm initially at that point of j of theta. Now at this point, again, depending on how much calculus you remember, you may get different amounts of intuition about this. If you don't remember any calculus, hopefully you follow some of this, but you'll still be able to implement the algorithm just fine without understanding the calculus. But if you remember some calculus, you may remember that the derivative of this, right, this derivative term, this gives you the slope of the function at the point, right? That's what the derivative of a function is, measures the slope of a function. And so because the slope here is positive, this term, dd theta j of theta, this is going to be positive. At this point, it's going to be positive. And so one iteration of gradient descent is going to update theta as theta minus alpha times some positive number. right? And so as a result of that, you're going to be decreasing theta, and thus you'll be moving towards the you'll be moving theta towards the minimum here. In contrast, let's say that's j of theta as before. In contrast, if I had initialized theta down here, right, then we'd be starting off at this point on j of theta, and at that point, well, not drawing this very well, but at that point, the derivative is going to be negative because this blue line here, right, this slope, the function has a negative slope at this point. And so, in particular, at this point, we would have that dd theta, j of theta, this is going to be negative. And so with this value of theta, initialized over here, you would have theta gets updated as theta minus alpha times some negative number. Right, and so alpha times a negative number is going to be a positive number, so you're going to be adding some positive number to theta, and so you'll be increasing theta, you know, to move theta further to the right, and hopefully to move theta towards the minimum over here. Finally, this also, hopefully this picture also gives some will help give some intuition about what happens with about the choice of the learning rate alpha, and why choosing this learning rate alpha can affect our algorithm. And in particular, alpha, the learning rate, controls the step size, right? In particular, it controls how big a step we take on this horizontal axis, on this data space. And so if alpha is too small, then what happens is, if you have a function that's j of theta, right, here's my initial value of theta. If alpha is tiny, then you end up taking, you know, tiny baby steps, right, just tiny little steps, and you might need a lot of steps to get to the minimum. So if alpha is too small, gradient descent can be slow, meaning they can require a lot of steps. And in contrast, if alpha is too large, then what happens, it turns out it can be even worse. So here's j of theta. Here's, let's say, actually, let me initialize theta over here. Right now, if alpha is too large, then I may end up taking a huge step like so, so that, you know, I actually end up at this point on the function. I take a huge step. And if alpha is too large, you can actually overshoot the minimum. And it turns out that from this point, if alpha is too large, you can actually overshoot again and, you know, end up even way too far to the right. So again, right, if this is alpha, you take a small step, medium-sized step, large step, way too large step. And it turns out that if alpha is too large, then gradient descent can actually diverge. Can diverge, or it can do a range of funny things, but it will not necessarily converge, or it may even diverge, just because you may, you know, keep on overshooting the minimum, and maybe by larger and larger and larger amounts. Okay, so hopefully that gives some intuition about what gradient descent does. Let me now ask you a quiz question, which is, suppose theta is at a local minimum of a function. So let me draw a function. And, you know, let's say I have a function that may have multiple local optima, right? So that's j of theta. That's my function j of theta, and the horizontal axis here is my theta axis. And let's say I start off theta at that point. And so let's say I start off theta over there at a local minimum. My question for you is, if I start off theta at a local minimum like that, what will one iteration of gradient descent do? So hopefully you got that one iteration of gradient descent will leave the parameter theta unchanged. And one way to see that, or one way to explain that, is gradient descent updates theta as follows, right? Theta minus alpha times, you know, dd theta j of theta. And so if you're at a local minimum, then sort of almost by definition, right, dd theta of j of theta at the local minimum is going to be 0. So at the local minimum, your function has, slope 0 is this horizontal slope, and so it has slope 0, and therefore theta gets updated as theta minus alpha times 0, and so theta remains unchanged. And this is why gradient descent at a local minimum will not change the parameters at all. And in fact, this also helps to, using this sort of intuition, we'll also be able to see how gradient descent can converge to a local optimum, say to a local minimum, even with the learning rate alpha remaining fixed. Okay, and here's what I mean by that. So suppose I have a function, as usual, j of theta, that I want to minimize. So that's j of theta. So let's say I start from here, right? Let's say I start here, take one step of gradient descent, maybe I'll end up stepping down here. Now you notice, so here's my minimum, right? Now you notice I'm a little bit close to the minimum, and so the gradient or the slope of the function at this point is actually a little bit smaller. So this point has a bit of a smaller gradient or a smaller slope or smaller derivative than where I started. And so the next iteration of gradient descent will end up taking a slightly smaller step. So I'm going to take a slightly smaller step to here. And now this new point, red point, has an even slightly smaller gradient. And so if you look at the update, theta gets updated as theta minus dd theta, j of theta, right? At this red point, the slope of my function is, and therefore this derivative, this is even a little bit smaller. And so my next step, I'm going to draw that in green, it's going to be even a little bit smaller, and so on. And then as I take additional steps, let's draw these in green now, right? Because as I get closer and closer to this global minimum, my derivative is getting smaller and smaller, and so gradient descent will automatically, having started off with a large step, the next step is a bit smaller, the next step is a bit smaller, and so on. And my steps will automatically get smaller and smaller as I approach the global minimum, or in this case, local global minimum. And so the algorithm will sort of automatically, start taking large steps and slow down and slowly converge to this local minimum over there. And just to write that down, as we approach a local minimum, gradient descent will automatically take smaller steps. Okay, so there's actually no need to decrease alpha, the learning rate, over time to get gradient descent to converge. Let's see, yeah, T. Sorry about the bad handwriting. And it's because as you approach the minimum, the gradient gets smaller and smaller, and so gradient descent updates automatically get smaller and smaller, which is why it sort of slows down as it approaches the local minimum until it actually converges to the local minimum. And it turns out that it will indeed converge, and it won't stop short, because so long as you haven't reached the local minimum yet, this derivative will still be, will still be non-zero, and so actually keep moving until it converges to the local minimum.